Uh, I would love to welcome you all. So my name is Abdulsalam Jakrut. I am the CTO and co-founder of Opinion Precision Life Science. We are a company that works in the domain of applied physics, artificial intelligence, as well as the different elements linked to health and wellness. So for today's presentation, I would like to share with you a perspective on where quantum technologies meet medical imaging, particularly breast cancer detection. This is a field where milliseconds and millimeters matter, and it's also a field where computational demands have reached limits that classical systems tend to meet. Quantum computing opens a completely new space of possibilities, and today we'll explore how close we are to leveraging it for real clinical impact. So we will be following this outline. We'll begin with the background both from classical computer vision and from quantum computing. And then we'll build the foundations of quantum vision, or QCV, and look at the current landscape of quantum machine learning in medical imaging. After that, we'll zoom on breast cancer detection across mammography, ultrasound, and MRI. And finally, we'll address limitations, future directions, and conclude with the key takeaways. So, the background for medical imaging and classical vision. Medical imaging is at the heart of modern diagnostics across MRI, CT scans, X-ray, ultrasound, and so on. Classical computer vision, especially deep learning, has dramatically improved tasks like classification and segmentation. Convolutional neural networks today can identify tumors, segment tissues, or flag anomalies with impressive accuracy. But classical models often require huge data sets, millions of parameters, and high-end GPUs. And even with all that, they sometimes fail where data is scarce or where patterns are subtle. This is exactly where we begin to see the potential of quantum methods. Quantum computing uses a different language. Qubits, superposition, entanglement. Gate-based quantum computers manipulate these qubits through unitary operations. Now, of course, today's devices are what we call NISQs, noisy intermediate scale quantum computers. They are imperfect and limited in qubit counts up to 1,000 and not yet ready for large-scale deployment. But they can run quantum algorithms and quantum machine learning circuits that, in theory, offer exponential representational power. And that opens up intriguing opportunities for image analysis. Here, I usually remind the audience about quantum computing, the fact that quantum computing isn't magic. It's just a new way of encoding, manipulating information. Quantum circuits can represent patterns, transformations, and correlations we cannot model efficiently with classical systems. This intuition helps when we move into quantum image representations. So, the first step in dealing with images in any in machine learning is, of course, how we encode or how we represent image. And in the case of quantum computing, there are currently in the state-of-the-art two different methods. The first one is Fourier representation of quantum images. It's one of the earliest and most influential quantum imaging coding schemes. It encodes pixel positions in basis states, which means ket 0 and ket 1, and pixel intensities as rotation angles. And you might ask, why does this matter? It's because in a single quantum state, you can store an entire image, and quantum operations can act on all pixels simultaneously through superposition. This is foundational for any quantum vision pipeline. The second way of representing images is the Necker method. It's for novel enhanced quantum representation. It takes a different approach. Instead of encoding grayscale intensities as amplitudes, it stores them directly in computational basis states. This makes measurements straightforward and often more stable. Studies show that Necker can achieve faster image preparation and better compression than FRQI. And this becomes critical when working with medical imaging, where pixel fidelity becomes essential. So the building block of the building block of every quantum machine learning enterprise is what we call variational quantum circuits, or variational quantum estimator. It's what also can be called the quantum neural network. They are the cornerstone of quantum machine learning today, and they consist of trainable rotation gates and entanglement layers. In the U operator you see here, we have a set of rotations and entanglement operators that are trained through the objective function. So it works very much like a classical neural networks, preparing the input states, applying the circuit measure, and optimizing the parameters. These circuits are small today, but they are already showing surprising learning behavior, especially on limited datasets. We come to what we call the convolutional neural network. So it's they borrowed a bit the intuition from classical convolution neural networks. So a convolutional layer takes small patches of an image and embeds them into qubits, applies quantum circuits, and outputs a transformed feature, which means that it's used as a filter on the image. And it's interestingly, studies show that convolution can help model generalize better on small medical datasets where classical CNN often overfit. In this case, as you can see, the quantum side of the operation is localized in the filter, and the rest is just the same thing as a classical CNN. And then we moved on to quantum convolutional neural networks. They go further through implementing actual convolution and pooling directly at the quantum level. And this is promising because QCNN architecture can exploit entanglements to capture global correlations with far fewer parameters, given that we can entangle multiple parts of the image, given that it is represented directly in the quantum state. It allows us to leverage this entanglement phenomenon in order to see more correlation and more relationships between the different features. In imaging tasks where small subtle signals matter, like microcalcification, this might one day provide a real advantage. So let's move on to what we call quantum machine learning, QML, in the medical imaging domain. So we have three kind of tasks that we are using. The first one is classification. So quantum classifiers have been explored for tumor detection, nodal classification, and other diagnosis tasks. Hybrid models with classical front-ends plus quantum layers seem to work best today. They leverage classical efficiency while adding quantum expressivity when needed. Although results are still early stage, accuracy gains have been reported across several imaging datasets. The second task is segmentation, clustering. It's harder, it requires pixel-level precision, and today most quantum work focus on quantum-inspired optimization methods useful for thresholding and clustering. 4 quantum segmentation networks are still in early research, but quantum autoencoders may eventually play a role. And the third task is anomaly detection. So this is the most exciting direction. Why? Because the quantum models, especially the quantum autoencoders, may excel at anomaly detection, given that quantum states naturally represent probability distribution in a high-dimensional Hilbert space. In medical imaging, this could mean earlier detection of subtle lesions or calcifications. We come here to the main subjects of today. So we'll shift our focus to breast cancer detection. One of the strongest results comes from a hybrid classical quantum CNN approach, where the author applied a classical CNN for feature extraction and the quantum classifier for final prediction. The hybrid model reached 84% accuracy, significantly outperforming classical benchmark, which was at 76.9%. And there is another study that is more promising that used quantum optimized support vector machines and achieved around 95% accuracy on CBIS DTSM dataset. These are very promising signals that quantum enhancements may provide value even in today's hardware. Moving to ultrasound results. Ultrasound is particularly challenging due to the noise and variability. So here, QCNN with convolutional layers outperformed classical CNN with the same architecture. The outperformance may look slightly, very slight, but remember, people, that these numbers are these percentages are representing the accuracy when we apply the model to real people's data, which means that it might be that this 4% difference can be the difference between living or dying for a person. What is interesting is that quantum layers improved validation accuracy, suggesting stronger generalization. And the takeaway is that quantum features might help models remain robust even when data is scarce or noisy. And the third task, it's about the different imaging approaches that beyond mammograms and ultrasounds. So for MRI, the work is extremely limited, mainly due to a higher data dimensionality, because as you know, the higher the volume of data, the dimension of the image, the more difficult is to encode it in so that it can be processed by a quantum computer. But quantum classical CNNs have been applied to structured clinical data with notable gains. On the SEER registry, a hybrid QCNN reached 93.2% validation accuracy, beating a classical CNN at 90% accuracy. These early successes show that quantum models are versatile, and not only for imaging, but also for future-based prediction. Here we come to limitations and challenges. So let's be candid. Quantum computers today are limited both in qubit count and noise level. Encoding medical images is expensive, and training deep quantum circuits is extremely difficult due to Baron-Plaitis. Most importantly, we do not yet have a proven, repeatable quantum advantage. We see promise and not yet proof. Acknowledging these challenges is key to guiding responsible development and deployment. For future directions, we need to focus on hybrid architectures that will continue to dominate in the near term. They will let us combine classical strengths with quantum expressivity. And we need also to work on better hardware, more qubits, better error mitigation that will unlock deeper quantum models. We'll also need more efficient encoding methods to handle high-resolution images. And ultimately, to move towards a clinical translation, we need validation on real patient data sets, integration with diagnostic workflows, and alignment with regulatory frameworks. Quantum imaging itself, quantum sensing, quantum MRI, may eventually merge with quantum machine learning, creating entirely new diagnostic modalities. Let me conclude with a few key messages. Quantum computer vision brings fundamentally new ways to encode and analyze images in early breast cancer detection. Initial studies show encouraging results, sometimes surpassing classical approaches, but we're still at the beginning. The hardware is young, the algorithms are evolving, and the path to clinical deployment is still long. Yet the potential impacts earlier detection, better accuracy, smarter decision support is enormous, and that's why this field deserves more attention today. Thank you for your attention. I'm at your availability if you have any question.